Alright, so in this video we go over section 11.6, solving nonlinear systems of equations. So we're going to solve systems of equations that contain equations that are not linear, like the ones that we did at the beginning of this chapter, So in this case, in the previous chapter, we were looking for points of intersection between lines or planes in the 3D in the 3x3 case. In this case, we're going to find points of intersection between parabolas and lines, parabolas and ellipses or hyperbolas. We're going to combine these the conic sections and finding their intersection points. So the two general strategies to solve this kind of nonlinear systems are, yes, again, substitution and elimination. But when do we use one? When do we use the other? So we would use the method of substitution when one of the variables has exponent has an exponent 1. We have like this example, and in this case what we do is do the substitution. So it would be a good idea to label the equations as usual, 1 and 2. Right? And so in this case I'm going to get equation 2 and I'm going to solve for x, because it has a negative. I can move it to the other side as positive, y plus 1. All right? And I'm going to get back to this equation almost at the end of the at the end of the solution to find the variable x. So what we are going to do, we are going to substitute x equals y plus 1 in the first equation where we see the letter x. All right, so that's what we do in this case. So I'm going to go quantity squared, that's x squared minus 3y equals to 1. Okay, so in this case, let's plug in the quantity y plus 1. And so that's y squared plus 2y plus 1. This is a binomial square, so that's a square of the first term plus 2 times the first and the second, and plus the square of the second term. And then minus 3y, keep writing the remaining terms. And it would be a good idea to combine like terms. Well, what are we going to have here? Negative 2y minus 3y. That's going to give us y squared minus y plus 1 equals to 1. And in this case, notice how these ones cancel. And we obtain an equation of degree 2 in which we can solve by simple factorization of a GCF. So y times y minus 1 equals to 0. So by the zero product property, y equals to 0 and y equals to 1. What is that going to mean when we get to solutions? So that means that we are going to obtain two order pairs in which the y coordinates are 0 and 1 respectively. All right, so now we need to go back to this equation again, the one I put in the box at the beginning of the solution, and we are going to find the x values for each corresponding y. So for y equals to 0 and for y equals to 1. All right, so we go x equals y equals to 0 plus 1 and x equals y equals to 1 plus 1. So plug in 0 and 1. And on the one hand, 0 plus 1, x equals to 1, and x equals to 2 on the second case. And we're essentially done solving this system of equations. So again, when submitting this solutions on MyMATLAB, you need to submit everything with commas. Let's do another one. Well, in this case, so even though we don't have really all variables one, well, we have this radical that, and in this case, we don't have to do anything, as in terms of like moving one variable to one side of the equation or the other. So all we do is directly substitute the square root of x where y is, because here is saying y equals the square root of x. So I'm going to work on the second equation, x squared plus quantity squared. In this case, the quantity squared equals the square root of x. Instead of y, I'm replacing with square root of x. And as you can see here, well, the square cancels the square root. That equals 6, and we get x squared plus x plus 6. Alright, and then actually equals to 6, not plus 6. And then all we do is move the 6 to the left hand side. X squared plus 6 plus x rather minus 6 equals to 0. Alright, let me fix this x real quick, and let me add this x. So we're gonna factor this trinomial. Hopefully we get a solution for it. So we're gonna look for factors of negative 6 that add up to positive 1. In this case, I will think of negative 2 and positive 3. By the zero product property, we get x equals to 2 and x equals to negative 3. What is that going to mean in this case? Well, that we are going to have two order pairs, two solutions, one in which negative 3 is the x of the solution, and another in which 2 is the y component of the solution. So we're going to do the same as we did in the previous example. Well, for x equals to negative 3 and for x equals to 2. Alright, so we're gonna go and plug this in the first equation. So y equals to the square root of negative 3 and y equals the square root of 2. Well, on the one hand, well, the square root of negative 3, it's not a defined number. Unfortunately, this one is going to be an extraneous solution because we cannot evaluate this for this radical function for negative values. So in this case, well, y equals square root of 2 is simply the square root of 2. So 2 square root of 2 is the only solution. This is not a solution. Alright, so let's move on to the next page. Let's look at another example. Alright, so x squared plus y squared. Let's see what we get. Equals 4, and x plus y equals to 3. Okay, so in this case, well, what do we have? We have, we can solve for, I'm going to solve for y in this case. Let me label the equations again. I mean, not that it helps a lot, but it's fine. So x plus y equal to 3. I'm going to solve for y. That's a negative x plus 3. Okay, and then I'm going to plug in this y equals negative x plus 3. I'm going to plug them in here. Alright, so we're going to go like x squared plus y squared, which is negative x plus 3 equals to 4. So negative x plus 3. Okay, and well, we're going to square the binomial. X squared plus the square of the first term, that's x squared, twice the first and the second, so that's in this case negative 6x and 9 plus 4. And then what do we get? Well, 2x squared minus 6x or equals to 4, and then move the 4 to the left hand side of the equation, subtracting. That's going to give us a plus 5. Alright, so now in this case we need to find a way to solve this equation. Well, factoring may not work because, well, 2 times 5, using the diamond method to factor the trinomial, that's a 10 and negative 6. Are there factors of 10 that add up to negative 6? Well, 10 and 1, that's going to give us 11, and well, actually 1 is, 11 and negative 11, it's not going to work. And then 5 times 2, that's 7, negative 7. No, that's not going to work using factoring. So we're going to use the quadratic formula in this case. Identify the constants a, b, and c. Let's recall what the quadratic formula in this case is. X equals minus b plus minus the square root of b squared minus 4ac. The whole thing divided by 2a. So x equals to minus negative 6. Recall that when we plug in the numbers from the on the quadratic formula that come from the equation, they come with a sign. And then plus or minus the square root of negative 6 quantity squared minus 4ac. Oh, not 4ac, actually the numbers. Never mind. So that's a, which is 2, and c, which is 5. Alright, the whole thing being divided by 2 times a, which is 2 times 2. X equals minus minus becomes a plus 6 plus or minus the square root of 36. And then 4 times 2, that's 10. 10 times 5, that's 50. 4 times 2 is not 10. 4 times 2 is 8 times 5. That's 40. Never mind. Yep. Silly mistake there. So that's 4. And look at this. What's going to happen? 6 plus minus the square root of negative 4. But what's going to happen here in this case? Well, we are going to have complex solutions. And for this reason, we are not going to have. This one is not going to be. It's going to be a no solution. No solution. Because the solutions are complex numbers, and we don't want complex numbers. We want only real numbers. Now, if you would like to visualize why is this not why it's not a solution, essentially there's no intersection points between these two equations. If we look at the graph of both equations number 1, let's define what they are. Isn't that the one on the top a circle, radius 2, center at the origin. Alright, that's what it is. And then we have a line or a straight line with m equals to negative 1 and b equals to 3. Let's plot those two. So alright, so what do we have? Well, the circle of radius 2 is going to look like this. It's not a perfect, that didn't come out perfectly, but well, that's basically the picture. And then the line y equals negative x plus 3. So we're going to go to the y-intercept, which is 3, and then the slope negative 1 over 1, rise over 1, or go 1 unit down, 1 like this, and it's actually not even going to touch the circle at all, as we can see from the picture. So that's what it means when a nonlinear system has no solution. That means the equations defined by this the graphs defined by these equations do not have any intersection points. All right, let's do a couple of examples using elimination. Well, elimination, we use that method when all variables are typically squared, but it also works for all variables being the same or same power. Now we can also use when all the same power, when they are all cubed, or when they are all to the 4th power, when they are all reciprocal powers, something like that. We can you know, we can use that method. So let's again keep in mind that when we solve equations by elimination, we want to have the same coefficient of the variable that we want to eliminate, but with opposite sign. And in this case, we don't have to do any multiplication, because if you observe the y's, those are already ready to be eliminated when we combine. So we add x squared plus x squared to give us 2x squared, and then 10 plus 1, which equals 11. And then we are going to solve this baby quadratic equation. X squared equals 11 over 2, and then x equals plus or minus, don't forget the plus or minus, for the square root of 11 over 2. All right. And then, well, you may not want to work with numbers like this, so you want to actually rationalize denominators. You may not want to work with radicals in the denominator, so that's x equals to plus or minus the square root of 11 and the square root of 2 divided by the square root of 2. And to rationalize the denominator, and that's going to give us x equals the square root of 11 times the square root of 2. That's the square root of 22. And square root of 2 times itself is simply 2. So what are we going to obtain here? We are going to obtain 2, well, let me write the solutions this way. Order pairs in which the x coordinate will be negative root of 22 over 2, and another one with the positive square root of 22 over 2. All right. So what are we going to do? We need to go back and find y. Okay, so in this case, for the same way we set it up earlier, we get, so for x equals negative root of 22 over 2, what do we get? So we can go back and substitute negative root of 22 over 2 in any of the original equations. Well, I'm going to choose the first one because everything is positive. Quantity squared plus y squared equals 10. And then substitute negative root of 22 over 2. But be careful when simplifying this. In this case, the square root of 22 squared, that cancels the radical, leaving us with the 22. And then the 2 squared becomes a 4. And notice that the negative sign squared gets canceled. So 22 over 4 plus y squared equals to 10, or 11 over 2. That's 11 over 2 plus y squared equals 10. Y squared equals 10 minus 11 over 2. And, well, you might want to find an LCD, multiply by 2 to get essentially 20 halves minus 11 halves. And that's a total of 9 halves. Y squared equals 9 halves. But in this case, if we keep moving using the square root property, y will be plus or minus the square root of 9 halves, which reduces at the same time as plus or minus the square root of 9, which is actually, well, let me write it down, over the square root of 2. The square root of 9 is a perfect square, so that's plus or minus 3 over the square root of 2. Square root of 2, square root of 2. That's 3 root of 2 over 2. Okay, that's what it is. So what do we have? So what are we going to have? Well, that's, oh, don't forget the plus minus. So we're going to have over here a plus or minus the square root of 2. Oh, come on. Plus or minus 3 root of 2 over 2. Okay, that's a 3. Yes, it's too light. Okay, and then let's do the other pair. So for x equals the square root of 22 over 2, you know, the positive one, I'm going to use the same equation, square root of 22 over 2 plus y squared equals to 10. Well, that's going to be essentially, if you look, I mean, yes, I'm going to write most of the same steps. 22 over 22 over 4 plus y squared equals 10, and then that's 11 over 2 plus y squared equals to 10. And then y squared equals to 10 minus 11 halves. But I mean, again, from y squared equals being 9 halves, that's going to be the same as what we did here. I don't want to repeat this again. This is going to be simply plus or minus 3 root of 2 over 2. So in this case, well, we're going to obtain plus minus 3 root of 2 over 2. Okay, but what is this solution going to mean? Well, in this case, and I'm going to use a different color to express the solutions, that means this is going to be split into two order pairs. Number one with both negative, and then one negative and one positive. And the last one, it's going to split into both x's to be positive, square root of 22 over 2, comma negative 3 root of 2 over 2, and both positives, square root of 22 over 2 and 3 root of 2 over 2. 4 order pairs. So this is the solution, not in terms of plus minus, it's actually in terms of individual signs. All right, so let's see. Let's move on to the next example. So you're going to see examples like this one that may contain, expanded polynomials. And then on top of that, some kind of rational expressions as well. So let's see, what about it? So when you look at an example like this, you might want to look at this part, look at the denominator of the second equation, and you might want to state that condition that x cannot be 0, because what happens if you plug in 0 in a denominator? Well, the expression gets undefined. All right, so what are we going to do in this case to move on through this example? Well, so I'm going to kill off the denominators by multiplying both sides by x. All right, yeah, this system looks a little bit crazy, but it's not as bad as it looks. So, well, in this case, the first equation remains the same, x squared plus x plus y squared minus 3y plus 2, and multiply everything by x. So x times x, that's x squared. X times 1 is x. X times this quantity, well, basically the x's cancel, and we get simply y squared minus y. So if you're thinking that we may have to complete squares or something, no, that's not what we are going to do. The solution to this system is going to be a lot simpler than it actually looks. And then, well, so in this case, we're going to move on through this by eliminating the square terms, because if you look at the x squares and the y squares, they both have the same coefficient and same sign. So in this case, it's going to be just enough to multiply by -1, and everything will be pretty much canceled. So the first equation remains the same. And then minus x squared minus x, basically the sign changes the sign of everything inside of the parentheses. Okay, let's combine like terms. So when we combine like terms, or when we combine the equations, x squared with x squared go away, y squared with y squared go away. Actually, x's with x's go away, and the only terms that we end up with is, are -3y minus y. Be careful here. Oh, actually, this was supposed to be positive. Yes, because 8 times a negative is positive. So -2y, and then this loner plus 2 equals to 0. All right, so what is this going to be? Well, so -2y equals to -2, and y equals to +1. All right, so what are we going to obtain? So in this case, we are going to obtain as a solution in which y equals to 1. Okay? Now, how are we going to find x? Well, the equations look a little bit crazy. So what we do is plug in y equals 1 on the first one, wherever you see the letter y, which is in these two terms. So as usual, so for y equals to 1, x squared plus x plus 1 squared minus 3 times 1 plus 2 equals to 0. Alright, so y equals to 1, plug in y equals to 1, and so we are going to get x squared plus x plus 1 minus 3 plus 2 equals to 0. All we do is simply combine these numbers, but observe that 1 plus 2 is 3. 3 minus 3, this whole thing is going to go to 0, those three terms. And we are going to get x squared plus x equals to 0. And then another easy equation to factor x times x plus 1. And that equals to 0. Using the square root property, not the square root property, the zero product property, x equals to 0 and x equals to -1. However, I'm concerned about the first solution, This one cannot be because of the restriction that we put over here due to this denominator. So the only legitimate solution would be x equals to -1. So -1 comma 1 will be the solution set, only one order pair. All right, let's look at other cases. These cases are a lot of fun when we combine exponentials, logarithmic, well, the trigonometric, in the end, we're not doing the trigonometric cases, so I'm going to leave that out. So, well, we have the system of equations in which one of the equations is log base x. That's kind of weird. The arguments to y equals to 3, and then log base x for y equals to 2. So recall, number one, that the definition of log base a of b equals to c means that a to the c equals to b. Right? So that's the definition that we are going to use for most of these equations, or in other words, raise both sides by the base x, that's the other way to get this done, So in this case, well, let's see. So I'm going to rewrite the system in exponential form rather than leaving it in logarithmic form, and the reason is because the variable x is the base, so I need to move it in a way that we can work on it. So we're gonna have then 2 to the y, 2y equals x cubed. And on the other hand, 4y equals to x squared. All right. So again, we're using this definition. The base of the logarithm becomes the base of the exponent here, and the argument gets get by themselves. So, well, a good strategy to solve this equation, this system of equations is, well, let's eliminate y by multiplying both sides of this first equation by -2, leaving us with -4y equals -2x cubed, right? -2x cubed, and then the second equation remains the same. So when combining the equations together, goodbye, 0 equals to -2x cubed plus x squared. All right, and then we are going to have another polynomial equation that we can solve by factoring. We can factor out x squared. We can factor out the x squared and end up with -2x plus 1. All right. And then solving this using the zero product property, we are going to have that x equals to 0 and -2x plus 1 equals to 0. Well, let's solve the baby equation over here. -2x equals -1 and x equals to 1/2. Okay, this solution is okay. X being the base of the logarithm is fine to be 2. However, recall the restrictions of the base. A in this case cannot be 0 and cannot be 1, because otherwise we're in trouble, so we cannot have base 0 or base 1. So the only potential solution for x will be that of x equals to 1/2. All right, and what are we going to do in this case? Well, just choose any of these two equations and solve for y. Well, I'm gonna do the second one. I'm gonna write for y equals x squared, and then y equals 1/4 x squared. So y equals to 1/4 times 1/2 quantity squared. And in this case, 1/4 times 1/4, which equals to 1/16. Final answer. So the solution set will be 1/2, 1/16. Let's do another one that contains logarithmic type of equations. Let's see. Let me put this one down here. And well, this one it's gonna be very interesting one, because this one has logarithms on different bases. So the logarithm, we have the natural log and we have a log base 2. So in this case, what we are going to do is use the other properties of logarithms that you might want to recall before moving on through this example. So you might want to recall that n log base a of x is the same as log base a of x to the n. That's the smackdown and basketball rule. And then we also have the sum and difference or the product and quotient rules. So this is what I'm going to do. I'm going to write these two equations separately. ln of x equals 5 ln of y. And I'm going to try to use different properties of logarithms to make these equations look a lot simpler than they were given. So number one, I'm going to use the basketball rule to make this coefficient, make this be a power of the argument. So in this case, ln x equals ln of y to the 5th power. And in this case, well, we can undo the ln's by raising or exponentiating both sides base e. And this is going to cancel e with ln, just the same way we did it a few chapters ago in the logarithmic and exponential equation section. So x equals to y to the fifth power. So we are transforming the system into, in a way, one that it's a little bit simpler. So this equation becomes x equals to y to the fifth power. Now let's work with second equation, that is log base 2 of x equals 3 plus 2 log base 2 of y. All right. So let's, number one, let's have all the logarithms on one side. So this 2 log base 2 of y, I'm going to send it to the left hand side as with the opposite sign. Log base 2 of x minus 2 log base 2 of y equals to 3. All right, in this case, our goal is to combine everything into one single logarithm equation to then apply the inverse function, which in this case is the exponentiation on a base 2. However, I cannot just combine these two logs together if one of the terms have a coefficient in the front. So what we're going to do, we're going to use the basketball rule, send it to the exponent. Without the sign, don't worry about the sign. Keep the negative between the two. That's fine. So log base 2 of x minus log base 2 of y quantity squared equals to 3. And now we are ready to apply, in this case, the quotient rule. And the quotient rule states that log base a of x minus log base a of y equals log base a of the quotient. So we're going to write this as a quotient. That's the rule we apply here. So log base 2 of the quotient x over y squared equals to 3. And in this case, we're ready to undo or to get rid of the logarithm by exponentiating. In this case, notice in the previous case I exponentiated base e because this ln is basically log base e. In this case we have log base 2, so we need to exponentiate on the same base as in the base of the logarithmic function. So goodbye logs, and x over y squared equals to the third power, which is 8. And last but not least, at least for this step, I can get x by itself, multiply both sides by y squared, or cross multiply 8y squared. All right. So x equals y squared, and x equals y to the fifth. So the second equation on the system will become x equal to 8y squared. All right. And so what are we going to do? Well, so in this case we can take a different alternatives. We can subtract the equations and get the difference between the two, or another alternative here is to simply do, because x equals y to the fifth, we can substitute it here. We can use the substitution method in this case. So when we do that, well, let's set y to the fifth power equals 8y squared. All right. So in this case, let me use the same color so you can follow the path here. So here we can subtract both sides y squared. So y to the fifth minus 8y squared equals to 0, and then use factoring for this equation. So in this case, so we can factor out y squared times y cubed minus 8. All right, on the one hand, y equals to 0, and on the other hand, y cubed minus 8 equals to 0. which is y cubed equals to 8, and y equals the cube root of 8. But notice, because the index of the radical in this case it's an odd index, we don't need the plus or minus, just the same way we did it with the square root or the 4 root or the 6 root, those are even indices. So in this case we just go like y equals to 2. And this is a legitimate answer. Unfortunately, well, in this case, this is going to be an extraneous solution. Do you see y cannot be 0 in this case? Well, let's go back to the original system. The logarithmic function, whatever, regardless of the base, whether it's natural logarithm or logarithm base 2, logarithm base 5, logarithm base whatever your number except 0 and 1, the logarithmic function is not defined for 0, so that's why we cannot get a solution here. So the only solution comes from y equals 2. So the logarithmic function is defined for positive integers, of course. So now we need to go back to any of the original equations in the system. I mean, whichever you prefer. So I'm going to go with the second equation right here. I'm going to write it below. X equals to 8y squared. X equals 8 times y squared. But what is y? That's a 2. So x equals 8 times 4, and x equals 32. So the final answer for the solution of this system of equations in logarithmic form is 32, 2. Final answer as an order pair. Of course, individually x and y, but we always submit answers as order pairs. Let's do a couple more examples. Well, this one, let's see how can we solve this system of equations. So ln of x over y equals to ln of x over ln of y. Keep in mind that this is not necessarily, this is not true. Keep in mind that's one of the most common mistakes when doing logarithms. When we have the quotient of a logarithm, we write as the quotient of the logarithm. But in this case, we are going to find the solution to this equation subject to x equals to 6, y equals to 4. But look at the way the system is kind of weird. It's given in a very, very weird way, I know. So, well, in a way that we can substitute, I mean, when you can simply substitute y equals to 8 equals to x to the 6. Well, on the first equation, we don't have any x to the 6, nor we don't have any y to the 8. So this is what we're going to do. What we're going to do, we are going to multiply the first equation by 6. I know, that's crazy. Where did I get that 6 from? Well, because in a way, when I apply the properties of logarithms, somehow I will make this x to the 6 appear, so we can substitute that y to the 8. All right, so let's, in this case, let's rewrite the system as 6 ln of xy equals to 6 times ln of x divided by ln of y. Be careful when multiplying both sides by 6. And then x to the 6 equals y to the 8th power. Alright, I know, let's, in this case, we are going to use the same property we use in the top, in the example at the top, the smackdown or basketball rule. So in this case, we're going to be in the need of doing the basketball rule. Turn the coefficient into an exponent. So in this case, well, this 6 right here will be the exponent of the whole quotient, because this x over y is the entire argument of this natural log function. However, this 6 right here will only be the exponent of this x, and this ln y will remain the same. All right. So, well, I think I'm just going to write this outside of the system. So that's going to be 6 ln of the quantity x over y, the whole thing to the 6th power, and then equals to ln of x to the 6th power over ln of y. Okay, now we are going to use the second equation to write everything in terms of y in this case. So x to the 6th equals y to the 8th power. So ln of x over y to the 6th power, that's that's actually in this case we can actually distribute the power to every element in the quotient here. So that's ln of y to the 8th over ln of y. All right. So that's ln of x to the 6, ln of y to the 6 as well. Right? Distribute the power. And then what are we going to do here? So we're going to use the same substitution to we also substitute that here. So ln of y to the 8th over y to the 6th. And then in this case, we're going to go back and do the smackdown rule. So I'm going to bring down this coefficient. I know we move it up for the 6, but in this case, we're going to go back to coefficient for a huge reason. You'll see why. Because 8 ln of y over ln of y. And in this case, see how these ln of y's get cancelled. All right. And in this case, on the left-hand side of the equation, y to the 8th power minus y to the divided by y to the 6th. This is the same as saying ln of y to the 8th minus 6, and that's ln of y squared equals to 8. So we are a step away to get y by itself. No, I'm not going to do a quadratic equation. What I'm going to do is also this smackdown process. That's going to be 2 ln of y equals to 8, and divide both sides by 2 to obtain, we need to go up here, to obtain ln of y equals to 4. So what we do next is exponentiate both sides of the equation on the base e. So cancel, cancel. Y equals to e to the 4th power. So now we need to find the x component of that. And well, in this case, we don't have to go to the logarithmic one. We can do it from x to the 6 equals y to the 8. So x to the 6th power equals y to the 8th power. And in this case, well, just back substitute over here, e to the 4th power. All right, e to the 4th power. And then power of another power, x to the 6 equals to e to the 32, e to the 32nd power. And well, in this case, x to the 6, to get rid of this 6th power, there's two ways. Either raise both sides to the 1/6 or take the 6th root. Well, actually, I'm going to do the raising to the 1/6. All right, in this case, cancel, cancel. X equals e to the 32 over 6. But 32 divided by 6, these are going to go, that's a e to the 16 over 3. So final answer as another pair, e to the 16 over 3, comma, e to the 4th. I know this is a crazy one, yet it's a really interesting type of exercise in which we put all these properties that we learned in the previous chapters on the logarithms and all those, put them together into systems. Let's do the last example for this section. That's going to be a very interesting one because in this case we are going to use another property that is not it's not the most common property to use in this case. That's the change of base formula. All right. So I'm going to work with both equations separately. In number one, when you have something like log base a of x, you can always change the base. So for example, you have a log base a, base 4. For example, you want to change it to another base. Let's call it b. We do it by finding the quotient of the log with the new base of x divided by a. So that's the change of base formula. That's the formula that we are going to use here. Change of base. All right. For example, just to refresh this. So for example, suppose that you want to evaluate log base 5 of 37, but maybe your calculator cannot do log base 5. Your calculator most of the times do log base 10 and natural log, which is log base e. So what you do is do log base 10 of 37 and divide by log of the new base 10, the one that your calculator will handle, of 5. Or you can do ln as well, ln of 37 over ln of 5. Or if for some reason you're working on an algebraic manipulation that requires another base, of course, you can do log base 13 of 37 if you want, as long as the new base is also in the denominator. And that's something that we are going to do in this case, because if you look at the first equation, we have a log base 7 plus a log base 49. We cannot use the addition rule, the addition to product rule for this pair of logarithms, because they do not have the same base. All right, so in order for these properties of log to work, they have to be in the same base. So we're going to do that trick. So let me write that down here. Log base 7 of x plus log base 49 of y to the 4th equals to 12. So I'm going to rewrite this log base 49 and I'm going to write it in simpler form into log base 7. And the reason why I do that is because the other equation has also log base 7. So log base 7 of x plus log of y to the 4th over log of 49 equals to 12. But we introduce this new base, in this case base 7. So we go from 49 to 7 basically. This one, the one in the denominator, well, we're gonna factor out the number 49 and write it as power of primes, and you will see how this reduces very, very nicely. Log base 7 of y to the 4th power over log base 7. Well, 49 is the same as saying 7 squared. You see what's going to happen here? Yes, log base 7 cancels the exponential base 7, and the 2 will remain there. So log base 7 of x plus log base 7 of y to the 4th power equals to 12. But don't forget this 2 in the denominator. Well, keep in mind that the dividing by 2 in this case is the same as multiplying by 1/2. All right. And we're almost ready to combine these two logarithms together, except that we need to have this coefficient as a power. using the the basketball rule. In this case, we're doing basketball. So log base 7 of x plus log base 7 of y to the 4th power times 1/2, which equals to 12. But what is 4 times a half? Isn't that a 2? Yes, it is. Y squared. Alright, and now we are ready to combine these logs together. But let me see, what did I do in my notes? In my notes, I left it like this. I think I left it like this, so don't worry about it. Now let's actually work with the second equation. The second equation, log base 7 of xy cubed equals to 6. So log base 7 of xy cubed equals to 6. So in this case, we are going to use the product rule. We have the logarithm of a product. We're going to write it as log of x plus log of y cubed equals to 6. But don't forget, the base is base 7. And well, over here, there's really not much to do, because if we compare these two equations, log base 7 of x, log base 7 of x, what we can do in this case, what do they have in common? Log base 7 of x. So what I'm going to do, I'm going to solve for log base 7 of x. And then I'm going to substitute this over here. So this will be substituted there. All right. So let me keep going here. So we are going to have 6 minus log base 7 of y cubed plus log base 7 of y squared equals to 12. So, well, in this case, I think I'd better, I'm going to write this in reverse order so it's easy to read. So that's 6 plus log base 7 of y squared minus log base 7 of y cubed equals to 12. So I'm gonna. I really didn't do anything interesting other than reversing the order of these terms, so we can easily see the quotient rule going on. So log base 7 of y squared minus log base 7 of y cubed, that becomes y squared over y cubed. So, and then I'm going to subtract 6. Log base 7, y squared over y to the 3rd power, that's y to the 2 minus 3 using laws of exponents, equals to 6. So 2 minus 3, that's log of base 7 of y to the negative 1 equals to 6. Okay, and then in this case, we are going to get rid of the logarithm by exponentiating on the same base as the logarithmic function, in this case, base 7. Keep in mind, this is not 7 times 6, this is 7 to the 6th power. Right, let me make it bigger so it actually looks like a base. And base exponential with logarithm, they go away, and we get y to the negative 1 equals to 7 to the 6th power. All right. Okay, what's the trick? What's the trick gonna be here? Well, let me go up here. I know we're going all over the place. Hopefully. So this y to the negative 1 is the same as 1 over y to the 1st power equals 7 to the 6th power over 1. All right, it's over 1. And then we can just find the reciprocal of this equation to solve for y, and y equals to 1 over 7 to the 6th power. But what is 1 over 7 to the 6th power? That's y equal to 7 to the negative 6. I know, crazy number, isn't it? Alright, now we need to find the x value. Where are we going to get the x value from? Well, the x value is going to come from here. So we are going to plug in, well, actually here where the y is. I was going to plug it in here, no, but it's going to be here. So let me rewrite the equation again. The solved equation, log base 7 of x equals 6 minus log base 7 of quantity y cubed. Okay, so what we do, this is basically going to be here. So 7 to the negative 6. Okay, power of another power, multiply the power. So 6 times 3, that's 7 to the negative 18. All right, and then x log base 7 of x remains the same on the left hand side. And then see what's going to happen here. Log base 7 cancels exponential function of the same base as the logarithmic function, but be careful because we are going to end up with negative times a negative. I'm going to leave the signs like that for a second. So that's 6 minus 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 negative 18. That becomes a plus. 6 plus 18, which equals to 24. So we are ready to solve this baby equation for x on a logarithmic notation. Let's do the inverse of the log again by exponentiating both sides base 7. And that's x equals to 7 to the 24th power. I know, crazy number. Don't even try to put it in the calculator. Most likely it's going to be some kind of overflow. It's not, or some kind of error. It's not even going to handle. So final answer, solution as another pair, 7 to the 24th power, comma, 7 to the negative 6th power. And this is the end of this video. It's a good place to quit. I know these last couple of examples were kind of crazy, but they were a lot of fun. So again, because this put together a lot of the properties that we haven't seen in a while. So I mean, this is what makes them fun to go over. So this is the end. I'll see you in the next video.